Hello everyone, I'm Hao Zhou from the Hong Kong Polytechnic University. I'm honored to present our paper NCScope, Hardware-Assisted Analyzer for Native Code in Android Apps. Android continuously dominates the smartphone market with over 17% share, and more apps use native code. A recent study showed that about 82% apps use native code for implementing advanced functionalities or achieving better performance. Many guidelines and research papers suggest that security-sensitive apps such as mobile banking apps should implement self-protection techniques in native code to prevent them from running in rooted devices and being tampered. Meanwhile, researchers discovered that malicious apps always abuse native code to perform anti-analysis. Therefore, tools for analyzing native code in apps are highly demanded. For researchers to characterize apps using native code, for store maintainers to uncover unwanted activities implemented in native code, and for app developers to diagnose bugs and performance issues. It is challenging to analyze native code in Android apps. On the one hand, the complexity of native code impacts the static analysis of native code. On the other hand, although many dynamic analysis approaches have been designed for inspecting native code in apps, the majority of them rely on three kinds of underlying techniques, including debugger, dynamic binary implementation, and emulator. Unfortunately, they usually generate incomplete and biased results due to their limitations in obtaining and analyzing execution traces and memory data with low overheads. Specifically, it is difficult for existing approaches to collect all executing instructions in an accurate and efficient manner because dynamic binary implementation and emulator may incorrectly recognize and emulate instructions, while debuggers can only access an instruction through the single-step method. Consequently, behaviors in native code may be mixed due to incomplete instruction traces. The existing approaches can be easily defeated by anti-analysis methods in native code because of their obvious footprints. For example, debuggers change status of the debug process. Dynamic binary implementation loads extra libraries and code to the app's memory, and the emulator has special files and properties different from real systems. Once detected, malicious apps will hide their behaviors. The existing approaches usually introduce significant overhead, which leads to biased profiling results. For instance, dynamic binary implementation and emulator-based tools cost more than 10 times slowdown. Such a slowdown has been exploited by malware to detect these tools through timing checks. To overcome these limitations, we propose a novel hardware-assisted analyzer named NCScope for native code in Android apps, which outperform existing approach in terms of effectiveness, efficiency, evasion resilience, and overhead. In the following, I will first introduce the background about hardware feature and the kernel component used by NCScope. Then I will introduce the design of NCScope. Meanwhile, I will introduce methods for NCScope to recover runtime function calls and data flow from the collected instruction traces and memory data to detect self-protection and anti-analysis methods and diagnose memory corruption bugs in native code. Subsequently, I will present our main experiment result. At last, I will summarize the work and state our future work. Here I will introduce the background about the hardware feature and the kernel component used by NCScope. NCScope exploits embedded trace microcell, short for ETM, a hardware feature of ARM platform to collect executed ARM instructions of the app running on real device. ETM tracks instructions executed by CPU via monitoring instruction buses with almost no overhead, and then outputs them as an ETM string. We find that all of the most popular 15 smartphones on FeatureMark are equipped with the ARM processors that support ETM. Meanwhile, NCScope uses extended Berkeley packet filter, short for eBPF, a lightweight in-kernel virtual machine for executing eBPF programs to efficiently obtain the memory data accessed by the app. An eBPF program can hook both kernel instructions and user space programs using prop infrastructure. Once the hooked instruction is being executed, the eBPF program will be executed to perform analysis-specified operations such as getting the register value or retrieving the memory data. It's worth to mention that since Android 9, both the kernel space prop and user space prop are supported by the system. Next, I will introduce the design of NCScope. As shown in figure, NCScope consists of two modules, an ARM version 8 based data collection module running ARM system loaded with eBPF programs whose version is no smaller than Android 9, and an analysis module implementing various analysis methods. Note that to minimize the additional overhead, we let ARM platform only perform data collection, while the data resolution to the analysis module, which runs in a separate personal computer. In order to recover high-level semantic information, such as code functions and their parameter values required for native code analysis, NCScope records the app instruction tracing and access the memory data. Specifically, taking and launching an app to be analyzed, NCScope instructs ETM to record the instructions executed by the app and invoke eBPF programs to retrieve the data from the app's visual memory. When the execution of native code ends, the data collection module outputs the instruction trace and the memory data to the analysis module for accomplishing various tasks, such as identifying cell protection and anti-analysis behaviors in native code, diagnosing memory correction bugs, and analyzing performance issues. Here, I will introduce more details on how NCScope traces instructions, collects memory data, and recovers runtime function calls. NCScope uses ETM to trace an app's executing instructions. In order to collect the relevant and necessary instructions for recovering runtime function calls, NCScope enables context ID tracing of ETM to just trace the instructions executed by the process of the app under analysis, so that the executed instructions of other apps will not be recorded by ETM. Meanwhile, since execution of a branch instruction may refer to a method invocation, NCScope enables branch broadcast tracing of ETM to record the target address of each executed branch instructions. The instruction trace alone is insufficient for native code analysis. For example, without the value referenced by the first parameter of the function open, we cannot know the file accessed by the app. Hence, NCScope leverages eBPF to collect the app's memory data at runtime. Specifically, NCScope instructs eBPF with eBPF programs to hook multiple system functions for getting their parameter values. Note that NCScope lets eBPF program record the PID value when getting the parameter values so that it can filter out the data irrelevant to the app under analysis. To bridge the semantic gap between the raw data in ETM stream and the high-level semantic information such as called functions required for native code analysis, NCScope recovers runtime function calls. Specifically, NCScope first constructs a mapping between each instruction address and the system function. Then, using the mapping, it finds the system functions called by the app according to the addresses of the instructions stored in the ETM stream. Note that NCScope treats the functions found within the execution of G9 onload and ArtQuick generic G9 trampoline as the functions called by the native code, because Android Framework calls these two methods when loading native libraries and just before the invocation of G9 function apps. Then I will introduce how NCScope leverages the collected data to detect cell protection and anti-analysis methods and diagnose memory correction bugs in native code. This table lists the detection rules we summarize for NCScope to identify cell protection methods in native code. In total, we collect 10 cell protection methods in 2 types, including root detection and tampering detection by studying the source code presented in the OWASP Mobile Security Testing Guideline and GitHub repositories. For example, to perform root detection, app can look for the executable files or APKs used for gaining or managing the root privilege from the file system because these files are typically found on rooted devices. To detect this root detection method, since the libc function including access, open, or state can be invoked to check file existence, NCScope records the values of their first parameters which store the file paths, and then inspect the obtained paths to find whether the app searched for root-related executable files or APKs. This table lists the detection rules summarized for NCScope to detect anti-analysis mechanisms in native code. Totally, we collect 12 anti-analysis methods in 5 types, including debugger detection, emulator detection, dynamic binary instrumentation detection, timing check, and dynamic code loading by referring to the code segment and technical details in research papers and the GitHub repositories. For instance, to detect the Java debug wireless protocol-based debuggers, apps can leverage non-reflection called the Framework API is debugger connected. To detect this debugger detection mechanism, NCScope analyzes the system function called by the app's native code from the recovered runtime function calls to determine whether the function is debugger connected was invoked. To diagnose memory corruption bugs, apps operations on memory data needs to be examined. Therefore, NCScope recovered the runtime data flow to diagnose use after free and double free bugs in the app's native code. To achieve its purpose, NCScope employs offline symbolic execution. Specifically, taking the initial program state, including registers, stack, and heaps obtained by eBPI programs and execution trace recorded in ATM string, offline symbolic execution recovered the runtime data flow by tracking the date values alongside each instruction in the execution trace. Note that for the data such as return values of system calls that cannot be inferred from the initial program state, they will be symbolized and then propagated through the execution trace. To detect use after free and double free bugs during this offline symbolic execution, NCScope monitors all calls to memory allocation functions and free functions and saves the allocated and free buffers to an allocation list and free list respectively. If the address accessed by a memory operation is in the free list, a use after free bugs found, and if the address of the free buffer is in the free list, a double free bug is found. Next, I will introduce our main experiment results. First, we analyze the actual overhead introduced by NCScope. The actual overhead introduced by NCScope comes from two aspects: tracing and executing instructions using ETM and retrieving memory data leveraging eBPF. To measure the actual overhead introduced by the two operations, for each operation, we run the native code test provided by the benchmark app Geekbench to get the performance scores. We also record the benchmark app's average startup time. Besides, we also calculate performance scores when both of the operations and none of the operations are conducted, and the latter is treated as the baseline. From the measurement result in the table, we observe that instruction tracing will not slow down the execution of app under analysis, and memory data retrieving only brings 1.175 times slowdown to the overall score. We further compare the performance of NCScope with DroidScope, a widely adopted emulator-based dynamic app analysis platform that can also perform instruction tracing and memory data retrieving. The measurement results show that either of instruction tracing and memory data retrieval of DroidScope brings obvious slowdown. When both the operations are conducted, DroidScope causes more than 41 times slowdown to the overall score, indicating that DroidScope incurs much more slowdown than NCScope. We also apply NCScope to conduct systematic studies on the native code-based self-protection method adopted by financial apps and the anti-analysis mechanisms used by malicious apps. To study the prevalence of self-protection methods, we apply NCScope to 500 randomly downloaded financial apps having native code from Google Play Store. We discovered that only 134 out of 500 financial apps under analysis implement at least one self-protection method in their native code, which implies that the security of financial apps is far from expected. Moreover, we find that rarely financial apps implement tampering detection method in their native code. To investigate the prevalence of anti-analysis methods, we apply NCScope to 300 malicious apps. NCScope identified that 235 out of 300 malicious apps implement anti-analysis methods in their native code, implying that Android memory commonly have anti-analysis behaviors. Moreover, we observe that these malicious apps commonly adopt debugger detection, timing check, and dynamic code loading to perform anti-analysis. We also apply NCScope to detect memory corruption in native code of apps adapted from a collection of open source test cases to show that it can aid memory corruption diagnosis. At last, I will summarize our work. In this work, we propose NCScope, a new hardware-assisted analyzer for native code in apps. We design methods for NCScope to detect self-protection and anti-analysis methods and diagnose memory corruption bugs in native code by recovering runtime function calls and data flow from the collected instruction traces and memory data. We extensively evaluate NCScope and use it to conduct systematic studies on native code-based self-protection methods ordered by financial apps and anti-analysis mechanisms used by malicious apps. We also apply NCScope to detect memory corruption in native code of apps to show that it can aid bug diagnosis and present a case study in our paper to show that NCScope can aid performance analysis. In future work, we will extend NCScope to support the identification of more behaviors in native code. That's all for the presentation, and thanks for listening.